Welcome to AI Paperslop. Imagine dropping a simulated Boston Dynamics robot dog into like a newly generated 3D environment.
Right, you load it up, hit play on your physics engine.
Exactly. And instead of walking across the floor, the robot just instantly falls straight through the ground into, an infinite void.
Yep, the classic collision failure.
Yeah, why does it happen? Because that beautiful photorealistic 3D environment you just generated was made of Gaussian splats. So visually it looks like solid concrete, but mathematically it's essentially just colored smoke.
Right, it's just a cloud of density.
Exactly. Well, today on AI Paperslop, we are breaking down a paper that turns that colored smoke into solid, physics-ready steel. The paper is titled TriSplat, Simulation-Ready Feed-Forward 3D Scene Reconstruction.
And it was from a pretty powerhouse team, right?
Yeah.
Researchers from Zhejiang University, ETH Zurich, Microsoft, and Monash University.
Yeah, heavy hitters. So here is the core insight right out of the gate for the ML engineers and researchers listening. We all know feed-forward 3D Gaussian splatting models are incredibly fast at generating novel views from sparse, unposed images.
Insanely fast.
But to use their output for actual physics simulation, you have to run these incredibly slow, highly lossy post-processing steps like TSDF fusion. TriSplat bypasses that entirely.
Right, just throws it out.
It replaces the Gaussians with oriented triangle primitives inside the feed-forward network itself. So in a single forward pass taking under 0.6 seconds, it predicts a fully textured, simulation-ready mesh.
Which you can drop straight into physics engines.
Yeah.
Like Unity or NVIDIA Isaac Sim.
Literally straight in. Okay, let's unpack this because this feels like a massive structural shift in how we handle 3D reconstruction.
Oh, it really is. I mean, it forces us to completely rethink the standard reconstruction pipeline. For a long time, the field has treated the rendering primitive and the simulation primitive as two entirely different, almost hostile entities.
Yeah. Right, like they don't want to talk to each other.
Exactly. You render a scene using these soft, forgiving, fluffy Gaussians because, well, they optimize really easily. Then you try to aggressively shoehorn that volumetric data into rigid triangle meshes after the fact.
Because physics engines demand hard boundaries.
Right. TriSplat looks at that pipeline and basically says, why are we doing this translation step at all? Let's just predict the triangles from the very start.
To really appreciate the mechanics of predicting triangles directly, we need to look at the massive bottleneck this is replacing. I mean, think about the last time you tried to take a state-of-the-art feed-forward model like AnySplat or DepthSplat or Yonasplat
Sure.
and actually use it for embodied AI or gaming. You feed the model a few sparse images, it shoots back this beautiful visual representation made of pipe maps or Gaussians.
Which look incredible.
They do. But as you pointed out, Gaussians are inherently volumetric. They are these semi-transparent clouds of color with radial fall-offs. They have absolutely no explicit surface topology.
Which is perfectly fine if your only goal is rendering like a cinematic video fly-through.
Yeah.
The camera doesn't care if the wall is solid, right? It just cares what color the pixels are.
Right, it's just a light trick.
Exactly.
Yeah.
But the moment you introduce an agent into that space, say a quadruped robot trying to find a foothold, or a virtual car whose tires need to actually grip the road.
A cloud of color is totally useless.
It's worse than useless. You fundamentally require collision checking and contact physics. And physics engines like Unity, Unreal, Isaac Sim, they run on explicit boundary representations. They calculate collisions based on intersecting planes, specifically triangle meshes.
So to bridge that gap right now, engineers have to drag those Gaussians through truncated sine distance function, fusion TSDF, or, use Poisson reconstruction to extract a mesh post hoc.
Yeah, which is painful.
It is. You build this incredibly fast sub-second feed-forward neural network, and then you just slam it headfirst into a post-processing brick wall. Looking at the data in the paper, TSDF fusion can take over 15 seconds per scene.
And worse than the time, it's highly lossy.
Oh, totally. You end up with fragmented geometry. You lose all these thin structures like shear legs or wires, and you get these bizarre floating artifact blobs everywhere.
Well, because it is a fundamentally destructive algorithmic process. I mean, think about what TSDF is actually doing behind the scenes.
Yeah.
It discretizes your entire 3D continuous space into this rigid voxel grid.
Right.
Then it evaluates the distance from every single voxel to an assumed surface, and finally it runs marching cubes over that grid to kind of guess where the mesh should be.
But you're taking the native rendering primitives, the specific Gaussians that the network meticulously optimized.
And you were just throwing them in the trash.
Yeah.
You discard your highest fidelity data just to force the scene into a format the physics engine can read.
Wait, let me push back on that for a second. What about surface-aware Gaussian methods? Because if you are listening to this and working in 3D vision, you are probably screaming at your phone right now about models like mesh splat or surface splat.
Oh, absolutely.
Don't those architectures already fix this exact problem by making the Gaussians act like surfaces?
If we connect this to the bigger picture, those methods are essentially half measures. I mean, yes, geometry-aware models like mesh splat do incorporate strong regularization during training.
They try to flatten the Gaussians out.
Yeah, exactly. They encourage them to align with the surface. But here is the critical limitation. They still rely on marching cubes, or TSDF discretization, to actually output the final usable mesh.
Ah, so you still hit the bottleneck.
You do. They are still volumetric approaches trying their hardest to impersonate surfaces. The underlying philosophy of TriSplat is completely different. It abandons the volume entirely.
So because converting Gaussians to meshes post hoc is slow and destructive, TriSplat just bakes the mesh natively. It's like baking a cake directly in the pan you want to serve it in, rather than baking a massive, shapeless block of cake, carving it out with a knife, and trying to ice the scraps.
That is a remarkably accurate analogy.
Yeah.
The network takes your sparse input images and directly predicts the final rendering primitives, the triangles themselves.
So how do they actually do that? The architecture they designed to pull this off is just a masterclass in modern vision pipelines.
It really is. They start the process by feeding the sparse, unposed images into a Dino V2 VTL14 backbone.
Let's pause on the Dino V2 backbone for a second, because why use that specific vision transformer instead of like a standard ResNet or CNN?
Well, standard CNNs are trained primarily for classification. They understand what an object is, but they lack deep spatial understanding.
Right, they see a dog, but they don't know where the dog is in 3D space.
Exactly. Dino V2, on the other hand, is a foundation model trained with self-supervision on massive amounts of data, and it inherently learns incredibly robust patch-level geometric features.
It just gets depth and boundaries natively.
Yeah, it understands correspondences between different views of the same scene almost out of the box.
Yeah.
Once Dino V2 extracts those rich visual features, TriSplat passes them through a local global attention decoder.
And this decoder alternates between two types of attention. First, you have intra-view self-attention, which does local spatial reasoning, basically figuring out how the pixels within a single image relate to each other.
Right.
Then it uses cross-view joint attention to aggregate multi-view correspondences. It's constantly checking the other images to confirm the 3D geometry. Like, I see a corner of a table here. Do you see the same corner from your angle?
And from that decoder, the network branches into 3 parallel heads to construct the scene. So head number 1 is the point map head.
Okay.
For every camera view, it predicts a dense local 3D point map. But it doesn't just output random 3D coordinates, it parameterizes these points so that their lateral position is strictly coupled with their depth.
Which mirrors actual projective image formation, right? Because if you just output unconstrained X, Y, and Z coordinates, the network might predict a point that doesn't even align with the camera ray shooting through that pixel.
Exactly, you get these weird floating ghost points.
Yeah. By coupling lateral position to depth, you geometrically anchor the 3D point to the specific pixel that observed it.
Then you have the camera head. Keep in mind, TriSplat operates in a pose-free setting. You just hand it images. You don't need external tracking software like CallMap to tell where the cameras are in the real world.
Which is a huge time saver.
Oh, totally. The camera head predicts SE3 camera poses relative to the very first view.
So by pinning the first camera to the origin of the world space, it completely eliminates global gauge ambiguity. The network doesn't have to guess where the entire universe is located. It just anchors the universe to image number 1 and calculates every other camera's position relative to that.
Spot on. Which brings us to the third branch, the primitive head. This is the engine room. For every single pixel, it predicts the raw attributes of a triangle.
Wow. Every pixel.
Yep. It outputs a density logit, 3 scale logits to define the triangle's size, a quaternion for its 3D rotation, spherical harmonic coefficients to handle the view-dependent appearance, how the light reflects off it,
Right.
and finally a blur parameter.
Because this primitive head is outputting literal triangles, mesh extraction stops being a 15-second algorithmic nightmare. You don't need TSDF. You don't need marching cubes.
None of it.
To get your physics-ready mesh, you literally just look at the output, discard any triangles with low opacity, and merge nearby vertices using a simple quantized position hash. That's it. You have a watertight-ish mesh in under 0.1 seconds.
It's remarkably elegant. However, predicting triangles introduces a severe geometric vulnerability into the learning process that simply doesn't exist when you train with Gaussians.
Ah, I was waiting for the catch. The orientation challenge. Because predicting triangles sounds incredible in theory, but in the muddy reality of gradient descent, triangles are incredibly unforgiving.
They really are. Consider the difference in their mathematical shapes. A Gaussian primitive is a soft, fluffy ellipsoid with a radial mathematically continuous falloff.
Right.
If the neural network predicts its orientation slightly wrong on, say, step 10 of training, that Gaussian still projects a plausible, soft, fuzzy footprint onto the image plane.
The target pixel still sees a bit of that fuzz.
Yeah, it compares it to the ground truth image and sends a useful gradient backward through the network to correct the angle.
But a triangle is a hard, rigid, infinitely thin plane. If a triangle is misoriented, it creates a harsh, hard-edged artifact. Or worse, what happens if the network accidentally rotates the triangle so it is perfectly edge-on to the camera?
Oh, it essentially becomes invisible.
Right. If it's invisible, the camera doesn't render it. If it doesn't render, it generates zero loss. If there is zero loss, there is zero gradient. The network has no mathematical way to know how to fix that triangle. It's just permanently broken.
And the authors proved this in their ablations. If you treat triangle orientation as an unconstrained latent variable, meaning you just let the network guess the rotation the same way it guesses Gaussian rotation, the entire model fails.
It just crashes and burns.
Pretty much. Triangles demand structural precision from step 1. Without it, the geometry F1 score drops by 0.057, and the mesh rendering PSNR drops by over 1.1 dB.
So how does TriSplat survive this? They use a technique called geometry-anchored orientation. Instead of letting the network blindly guess the orientation, they calculate raw geometry normals directly from the 3D point maps using finite differences.
And finite differences is a brilliant application here. Think of the 3D point map like a topographic map of a mountain. To find the slope of the mountain at a specific spot, you look at the point directly to your right and the point directly in front of you.
You take the horizontal derivative and the vertical derivative. Like if I take one step to the right and the elevation goes up 3 feet, I know the horizontal slope. If I step forward and goes down 2 feet, I know the vertical slope. You take the cross product of those two vectors and boom, you have a normal vector pointing straight out of the surface. You use that normal to physically align the triangles so it is perfectly flush with the geometry.
It provides a massive structural prior. But of course, this introduces another hurdle. During the early stages of training, the point maps generated by the network are terrible.
Because they haven't converged yet.
Right. The topographic map is full of spikes and craters, which means those finite difference normals are going to be incredibly noisy.
So to fix that noise, they introduce a lightweight UNet to refine the raw normals. This UNet takes the raw normals, some smooth versions of those normals, the RGB image and the depth map, and it learns to smooth out the finite difference errors. But here is the detail I absolutely loved. The output layer of this UNet is zero initialized.
Yes. That zero initialization is vital for stability. I mean, think about what happens if you initialize a neural network layer randomly, which is the default in PyTorch.
Right, usually it's just random noise.
Exactly. On step 1 of training, that UNet would output wild, random perturbations. It would take your mathematically correct finite difference normals and scramble them in random directions before the main network even had a chance to learn anything. It would completely disrupt the rendering process.
But by zero initializing the output weights, the UNet starts its life as a perfect identity mapping. It does nothing. It just passes the raw normals straight through. And then as the training stabilizes and the loss function guides it, the UNet slowly wakes up and starts applying gentle corrections.
It's so smart. Yet even with a UNet, the first few thousand iterations face a severe chicken and egg problem. Bad point maps cause bad normals. Bad normals cause the triangles to face the wrong way.
And if they face the wrong way, they render poorly or become invisible.
Which means you get zero gradients.
Right. And if you get zero gradients, the point maps never improve to fix the normals. The system is just deadlocked.
Which leads to their intervention to break the deadlock, the mononormal bootstrap. They warm start the orientation using a completely separate pre-trained monocular normal estimator. Specifically, they use a model called OmniData DPT. They compute these teacher normals offline before training even starts. Then, using a cosine schedule, they blend these teacher normals with the model's own predicted normals. decaying the teacher's influence over the first 20,000 steps.
Now, what's fascinating here is how they apply this teacher normal. Because in a standard architecture, if you have a teacher model, you usually just add a loss term at the very end of the pipeline. You let the network predict its normal, compare it to the teacher normal, and penalize the difference. But TriSplat doesn't just do that.
Right, because a loss function at the end doesn't fix the zero gradient problem. If the triangle is invisible because it's edge-on, a loss function at the tail end of the network can't save it. What's fascinating here is what TriSplat actually does. It injects that mononormal bootstrap directly into the forward pass. The blended normal is fed directly into the local tangent frame construction. The teacher normal physically reaches into the network and forces the raw primitive to rotate and face the camera.
So it shapes the rendered output itself. By physically orienting the triangles during the forward pass, it ensures they cast sensible footprints on the image plane. They remain visible, they render correctly, and most importantly, they receive rich gradients during backpropagation.
It's a brilliant way to stabilize a representation that is fundamentally hostile to early-stage optimization.
But even with perfect orientation, you are still training with hard-edged primitives from scratch. Here's where it gets really interesting. Even if a triangle is perfectly aligned with the surface, if its predicted scale or position is slightly off early in training, it might miss its target pixels entirely.
Exactly.
A fluffy Gaussian has a soft tail, it overlaps the target pixel, gets a gradient, and is pulled into place. A rigid triangle misses the pixel, gets a gradient of 0, and learning stalls. So how do they tame the hard edges?
Well, they employ a soft-to-crisp curriculum via a custom differentiable triangle rasterizer. They're essentially tricking the network. They schedule two complementary softness parameters, opacity and blur, to transition the representation from forgiving blurred blobs to strict, sharp surface elements over time.
They let it train like it's using Gaussians at the start and slowly pull off the training wheels?
Yeah, that's exactly what it is.
Looking at the opacity scheduling, they use a nonlinear mapping where an exponent ramps up over time.
And by increasing that exponent, any intermediate density values are aggressively pushed toward either 0 or 1. If a triangle has an opacity of 0.5, raising it to a higher power squashes it toward 0. They are progressively binarizing the opacity field.
Makes sense.
And they pair this with a temperature factor in the rendering equation that ramps up to further sharpen the distribution, acting sort of similar to temperature scaling in a softmax function.
And at the exact same time, they do blur scheduling. Triangles start their lives with a massive blur parameter. This gives them broad, soft, overlapping footprints. They have dense gradient coverage, acting exactly like Gaussians.
Very forgiving.
Yeah. But over 16,000 steps, that blur parameter linearly decays. The footprints tighten up, the blur vanishes, and you are left with strict, crisp, boundary-defined surface triangles.
By scheduling both opacity and blur synchronously, they bridge the gap perfectly. They achieve the stable, forgiving early optimization of volumetric methods, but they arrive safely at the strict topology required by physical simulators.
Okay, let's look at the payoff. The architecture natively outputs triangles. It anchors the orientation using finite differences to prevent artifacts, and it uses progressive sharpening to make the hard edges trainable. Does it actually beat the Gaussian baselines and the metrics that matter to you and your engineering team?
The results are highly compelling, specifically because of how they benchmarked it. They evaluated on Real Estate 10K, the DL3DV dataset, and ran zero-shot evaluations on ScanNet.
Let's talk about mesh rendering quality. When the exported meshes are actually rendered out, TriSplat achieves 24.69 dB PSNR on Real Estate 10K. The absolute best Gaussian baseline they tested, Jonas Flat, only hits 21.94 dB.
That is a huge gap.
Right. Why do Gaussians fall so far behind when they usually dominate rendering competitions?
Well, this raises an important question about vanity metrics in embodied AI. If you evaluate the Gaussian models before mesh extraction, what we call primitive rendering, they look fantastic. They score very high. But primitive rendering scores are utterly meaningless if your end goal is dropping the scene into a physics engine.
Because Unity doesn't run on primitive rendering scores. Unity runs on meshes.
Exactly. When you force those high-scoring Gaussian baselines through TSDF fusion to get a usable mesh, they suffer from severe primitive-to-mesh degradation. The discretized marching cubes volume throws away the very primitives that produce the high-quality image.
Oh, wow.
Yeah. But TriSplat has almost zero degradation. Right. Why? Because its rendering primitives are the mesh. What you render is exactly what you export. No information is lost in translation.
And the speed difference is staggering. End-to-end inference for TriSplat on a 6-view input is 0.57 seconds. The fastest Gaussian baseline, any splat, takes 18.7 seconds. Why? Because while the feed-forward network itself is fast, that TSDF fusion overhead scales with the physical volume of the scene, not the network size.
Right, it's a massive bottleneck.
At 24 input views, TriSplat is up to 249 times faster than volumetric cost volume methods like depth splat.
That speed and fidelity translate directly to immediate utility. The authors prove this too. They literally dropped the TriSplat exported meshes straight into Unity and NVIDIA Isaac Sim.
No manual cleanup.
None. Without any manual cleanup, without any topology fixing, and without format conversions.
They ran rigid body ball drops, object stacking, and had a simulated legged quadruped robot navigating over the generated terrain. The robot's foothold planning directly leveraged the mesh surface normals that were predicted in that single sub-second forward pass.
It proves that simulation readiness can be a native, inherent property of the neural representation itself, rather than a messy problem we try to solve with downstream conversion algorithms. Escaping the volumetric bottleneck is just a massive leap forward for any pipeline requiring contact-rich interaction with dynamically generated environments.
So what does this all mean for you as a developer or researcher? TriSplat successfully bridges the gap between the blazing speed of feed-forward view synthesis and the strict topological requirements of physical simulators. It completely bypasses the TSDF fusion bottleneck by betting entirely on the humble triangle.
That's a huge shift.
But it does leave us with a fascinating final thought to explore. Right now, TriSplat ties the triangle density directly to the input image resolution. This creates what is essentially a non-manifold triangle soup.
Right, it's not perfect geometry yet.
No. It's good enough for rigid body physics and collision detection, but it's not a perfectly watertight mesh. If future iterations can incorporate topology-aware export and adaptive tessellation directly into the forward pass, could we see real-time feed-forward generation of fully watertight, finite element-ready assets generated instantaneously as a robot moves through an unknown space?
Imagine that.
Imagine a drone mapping a damaged building, rendering the environment, and simultaneously generating structural stress models on the fly in under a second. We're not there yet, but TriSplat just laid the foundation. That's all for today's dive into AI paper slop. See you next time.